This program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest UCTV programs.
Good evening, everyone. Welcome to Science at the Theater, sponsored by the Friends of Berkeley Lab. My name is Jeff Miller. I'm head of public affairs at the lab, and I will be your host for this evening. Tonight's show is entitled Climate Change is Here, Now What? When we say now what, we really mean that. The last time we did a climate change show a few years ago at Berkeley Rep, the news was not good. Everyone left in despair, and we don't want that to happen tonight. Tonight is going to not be about despair. Tonight's going to be about resilience and solutions and adaptation and imagination. To that end, we've divided the program into 4 segments. The first will be about where we are now. The second is where we're headed. The third and fourth will be about the solutions, the now what part, from a regional and institutional perspective. As you heard at the beginning, there will be questions at the end of each of these segments and a break with Science at the Theater tradition if you've been to one of our shows before. We ask that the questions be short and tailored to the discussion we've just had, if possible. We will be taking questions from you, obviously, and also from our live stream audience, and we have received some questions via email as well. Our guest this evening is Berkeley Lab's Bill Collins. Bill is Director of Climate and Ecosystem Sciences at the lab. He's a member of the Nobel Peace Prize-winning panel on climate change, and he also is Director of the Climate Readiness Institute, an organization you will be hearing more about this evening. So with that, please give Bill a very warm welcome. Welcome, Bill.
Thank you, Jeff.
It's
pleasure to be here.
So let's begin by a common phrase we hear in all the meetings that we go to. Let's take a look at things from the 30,000-foot level. But in this case, I want you to go way into space and look back at the planet from a different perspective. And in thinking about that, think about incorporate into your answer the fact that we have more carbon being pumped into the atmosphere than we've had in the last 56 years. That we may be facing a scenario, at least in popular literature and scary stuff, that we're looking at a world that's going to look like Waterworld from the movie, where we're all driving around in boats and looking for food, or we're looking at a scenario that where Mars, like Mars, we have a desiccated planet. And before you answer, one more thing. I want you to think about you're testifying in front of a congressional committee, and they're asking you, Dr. Collins, please give us the state of the planet right now. What would your answer be?
The state of the planet is good.
Okay.
But we are changing it pretty dramatically. And you asked about the view from space. We can see the change from space now. It's quite evident. It would be evident even if you were looking at the Earth from another solar system, quite literally, that the Earth is different than it has been in the past.
How so? What would you see?
Well, one of the things that Earth does now because of mankind is it emits all kinds of radio waves and other energy that the sun doesn't emit. So you could tell if you were in a solar system several light years away that the Earth was inhabited because it's emitting far more radar waves than a sun like our own sun could possibly emit. So you know immediately the Earth is inhabited. But you could also tell, if you had measurements that went back a little ways, that we've changed the composition of the Earth's atmosphere very dramatically. So if I were testifying to Congress, I would say we have really great information that we have altered the Earth, we mankind. We have entered into an era where man is a bigger actor, or at least as big an actor on the planetary stage as nature herself.
I'm going to ask you about the human activity a little later in this segment, but for now, what would you say about sea water rise and arable land and the disappearance of islands, whole nations at this point? Would that be part of your testimony, Dr. Collins?
There are a number of countries around the world that are very concerned about this issue of sea level rise. I've done experiments in some of them. These are countries that are built on coral atolls where the average height above sea level is just about a meter. And we expect to hit a meter at least during this century. So some of these countries are beginning to experiment with building artificial islands. Some of them are building artificial walls. Some of them are planning an exit strategy. So this has become a real issue among island nations. It was a very big issue during the recent Paris talks.
Okay. So this week, I don't know how many of you saw this, but the James Hansen, who's known for his climate work, published a report that said that the climate change is actually worsening at a much more rapid pace. There's going to be catastrophic changes, even these giant ocean waves that are going to be heaving boulders onto the landscape. So what are your feelings about that? Is this sort of an extreme interpretation, or is that something that's real?
I knew you were going to ask me this question about the Hansen's paper. I think to his credit, he went the right route. He published this in the scientific literature. It's going to take a while for the community as a whole to sort out the claims in that paper. And I think when we do an assessment of climate change, it's not based on one particular sort of X-Files type paper where the truth is out there and we were just waiting to have the truth revealed to us. We're really going to have to examine the findings in that paper over time to understand them. But Jim partly did this, I think, in order to reveal to people and to shock people into understanding how bad climate change could be. The information that politicians have needed to understand the severity of the problem has been out there for decades. And the fact that, even setting aside the Hansen paper, that people aren't awake at night worrying about this problem is kind of stunning. And I think we'll come back to this point at the end of our discussion this evening. But
okay.
There's plenty of information out there right now that says you should be extremely concerned about maintaining present course. And Jim's paper is just sort of one more log on the funeral pyre for maintaining the present course of action.
Well, let's talk about that disconnection for a second. Let's talk about real estate.
Okay.
So in preparation for this, I decided, let me just take a look at Miami Beach.
Mm-hmm.
Let's look at real estate there, and let's just see what is being offered and at what price.
Mm-hmm.
So ironically, or coincidentally, most of these properties are on Collins Avenue in Miami Beach.
Thank you. There's no conflict of interest here.
And I just tallied it up. There was something like 614 properties, and tallied all the estimated worth, something $70 to $80 million. So what does this tell us about the disconnect, and what is this real estate actually going to be worth by mid-century, do you suppose?
Great. Well, Florida is already experiencing flooding in a number of its communities now because of sea level rise. And this is partly because of the geology of Miami and the areas around it. Florida and the whole eastern seaboard are facing a real game changer if we experience 2 meters of sea level rise. That's going to permanently alter the geography of Florida. And the Florida and many other coastal communities on the eastern seaboard, including, I'm sorry to say, North Carolina, are exhibiting a deep form of, see no evil, hear no evil, say no evil. And that's not a workable strategy.
So is the sea level rise that we hear, is it going to be 6 feet? How do we know? And how can we predict at this point?
Okay, well, one thing, we can set a floor underneath it, and then the floor is already a pretty severe floor, but the floor is based on the fact that water expands when you heat it. And we have a pretty good idea of how hot the ocean is going to get this century if we continue business as usual. That equals about 1 foot of sea level rise. If you then take what we know is happening to land glaciers and to the ice sheets, that triples the sea level rise. It brings it up to just about 3 feet or about a meter. Then if you start to trigger instabilities in the ice sheets, which we think is a real possibility, and we could come back to Greenland in just a moment, then a meter is sort of again becomes a new foundation, and you start building from there. Just to amplify, I'm going to remind you, Jeff, that our point this evening is to convey a message of hope.
Oh, we're getting there. We're going to get
Okay.
there. We're going to get there. Please don't worry.
Yeah, I do want to. Yeah, I'm going to bring you back to that point. But Greenland just this year opened up a new pathway for releasing ice into the ocean. There are 4 pathways out of Greenland into the ocean. One of them, which was featured in that movie, the movie Chasing Ice, was the one that was really prominently featured. But a new one just opened up in the northeast corner, and so we're going to see a major contribution from Antarctica and Greenland to sea level rise this century. And they're already contributing. They're already contributing. A quarter of the sea level rise we're measuring right now is due to is due to Greenland and Antarctica.
Okay, well, to shift gears just for a second, because I'm trying to use this opportunity this evening to cover a lot of ground. There is confusion still about the immediate impacts and then the difference between weather and climate. So could you just explain that for everyone at this point?
Difference between weather and climate?
Yes.
So climate really, let me take a step back here and answer in perhaps a different question than you wanted me to answer. The human species has relied on having very stable and predictable zones where we know what we can grow, we know what will work in terms of agriculture, we know what will work in terms of cities, and we've enjoyed that since the dawn of agrarian agriculture 10,000 years ago. We've had a very, very stable climate. And what that's meant is that California has experienced a Mediterranean climate. So some years, like this year, we have a lot of rain. Other years, we don't. So the variability from year to year is the weather. That very predictable pattern where you know that we can grow grapes here, and the grapes will do very well. That's the climate. If you go to Europe, they've known that they could grow grapes really well in southern France since the time of the Romans. That's something we've relied on as basically as the foundation for our civilization. What we're doing right now is we're pulling the rug out from under that foundation.
So this would speak to that point about how much is already factored into climate change, which we can't change, and then what might happen in the future.
Well, this is one place where I'll re-inject a little bit of hope into the conversation. So if we instantly could freeze the amount of CO2 and other greenhouse gases in the Earth's atmosphere and just hold them steady, what we would see over this century is about half a degree Celsius, or close to about 1 degree Fahrenheit of temperature rise. That is pretty mild compared to what will happen if we maintain a business as usual scenario. So that you should consider that 1 degree Fahrenheit is being baked in from what we've already done to the climate system. That's not a huge amount of climate change. It's survivable. But the problem, just coming back to this issue around that serving as a foundation, what we're doing is we're accelerating the pace of change.
Okay. So given all that, I know you did not attend the Paris meeting in December.
I was busy working on trying to solve the problem.
Trying to solve these problems in the Berkeley Lab tradition. So why are all the people in Paris so happy? Why were they smiling?
There was a breakthrough there in terms of the structure of the agreement. And I think the agreement has been, one way you can tell it was successful is that it was criticized from almost all sides. That's often a measure of success around a compromise. The agreement is not, it isn't everything it should be, but what it did do is set up a new foundation for agreements going forward. Essentially said to everyone, bring in your best shot as to what you can do, and we'll tally this up and see what this amounts to. And so in contrast to previous attempts at negotiations, which had gotten completely wrapped around the axle of inequities in historical emissions versus future commitments, in this one, 170 countries came, and only 10 countries that came did not come forward with agreements to participate. About a third of the countries said, we don't have a technological fix, but we'll agree not to log our forests. We'll keep that carbon sink in place. So that was a big step forward, because you got many, many, many members of the UN General Assembly agreeing to be part of the solution. Was it enough?
Yeah.
No. But you've opened the door now so that people realize that they can come to these agreements and perhaps take a bigger lift. And that, creating a structure which creates a path forward for successfully more stringent measures, was the other big success coming out of Paris.
And wasn't there a monitoring component of, well, like every 5 years, they're going to be monitoring progress?
There is a monitoring component, and it's set up as a ratchet mechanism so you can't slide backward. That's another very important piece of the agreement. The countries are only allowed to go forward, they're not allowed to backslip.
I have read figures as high as like $44 trillion to switch out of a fossil fuel world into a renewable world. And I ask that question because when you see pictures coming out of Beijing of folks running in this horrific air, and you think about what might it take to fix that problem, and it seems so inexplicably tied into their economy that to fix it, are we not risking the undermining of the Chinese economy itself, which has other consequences, and there are other ramifications for the U.S. and as well in terms of our fear that it's going to, some people say that it will ruin our economy to go to a completely renewable society. So is it really possible to reduce greenhouse gas emissions without wrecking the economy at the same time?
Yes, there's a part of the IPCC assessment, not the part that I dealt with, but the one that deals with measures to mitigate climate change that has looked very hard at this. And you quoted, the number you quoted was sort of a number that's integrated over probably decades to a century worth of investment in clean energy. If you look at the dollar expenditure on an annual basis, it's something on the range of 3 to 5% GDP. It is not, an economy killer by any stretch of the imagination. And I think, rather than talk about hypotheticals, let's talk about some really shining successes in this story.
Yeah.
Germany made a commitment a while ago to switch to renewables. They are now 30% renewable. Germany is not doing badly as an economy. Let's take California as an example. Thanks to the energy crisis in the 1970s, California committed itself to halving the carbon intensity of its economy. So we now expend half as much carbon for every dollar produced as the rest of the country combined. And I would also argue that California is doing pretty darn well. So those are two great examples, one local, one international, where switching to clean energy has improved environmental quality, and the people who have done it have really made out like gangsters. But I was going to actually accuse you of channeling the Chicago School of Economics here just a moment ago, because the only thing you mentioned was the economic downside to switching. There's a huge economic downside to not switching. And I think that those costs are ones that also have to be factored into these considerations. And those are very real.
So give me some examples.
Well, you were just quoting me a moment ago, the real estate prices of just one street in Miami, right, that might go underwater. So imagine taking large portions of Florida and rendering them almost uninhabitable, and ask yourself what the dollar value is of that. And then multiply that by coastlines around the world. I mean, we're looking at displacing, even with a meteor sea level rise, over 100 million people, probably close to 200 million off the coastlines. That costs money too.
Yeah, we can use, put them in tents, perhaps? Is that what we're going to do?
Well, I'm not going to go there, but
and maybe we can manufacture tents. Maybe that's what we should be doing at this point.
No, I think, but this, in all seriousness, you look at other countries that are taking this very seriously, like the Netherlands, and the Netherlands is now busy exploring how to put housing on pontoons. And I am happy to say, by the way, that San Francisco is partnering with cities in the Netherlands to figure out how to adapt here. Because it's going to be a very serious issue.
Yeah, we will talk about the regional issues a little later in the evening. But I do want to switch now to focus a little bit on California. So snowpack is, of course, a huge issue for us. And when we talk about snowpack, we're talking about water. So the slide that we have shows, the diminished role of snowpack in California. So from a California perspective, and then the larger issue of water and the climate change, we often don't zero in on that. We talk about sea level rise, but we don't talk about the distribution of water and the system.
Right.
So could we talk about that for a little bit?
Sure.
What challenges California faces?
Well, one of the silver linings of climate change is that it's putting water vapor into the Earth's atmosphere. The sort of the dark cloud that silver lining is surrounding is the fact that where the water is falling is moving.
Mm-hmm.
So the storm tracks that have fed water into California for its entire recorded history, in fact, its entire geologic history, those storm tracks are moving northward. We can measure that from space.
Mm-hmm.
We can measure it from the ground. And at the same time, as we make the climate hotter, the precipitation that does falls as rain rather than snow. So the problem is that in California, we have sort of two time-release sources of water that we can, basically water banks. Those are the huge aquifer under the Central Valley,
Mm-hmm.
and which is a long-lived bank, and then a shorter sort of shorter-lived bank, which is the snowpack. And because when the climate heats, it's more likely that the precipitation will fall as snow rather than, fall as rain rather than snow.
Mm-hmm.
We're depleting that second bank. California is going to have to adapt to the loss of that bank. And this paces, it's a pacing issue for us. It's a real challenge to our water agencies. And how California deals with that issue is going to be one that's going to test our ability to come up with cooperative and societally and environmentally sustainable solutions.
Okay, I want to close out this first segment by dealing directly, because it obviously speaks to your research, which I'm sure you're going to discuss. But there are still some, of course, who argue that human activity is not responsible in any way for climate change. So I know your research addresses that directly, so I'd like you to explain to the audience about radiative forcing and other things that you've studied. And
Sure.
Let's kind of put that to bed once and for all, and we'll get it on tape.
Sure. There are two ways that we know that mankind is causing climate change. The first is that we can compare what's happening now to the geologic record. And in the geologic record, the big actors were changes in the sun and changes due to volcanoes. Those both produce signatures in the temperature of the climate system that don't match what we're seeing now. The only way that we can explain the temperature signals that we're seeing now, and this is the fact that the lower atmosphere is warming and the upper atmosphere is cooling, the only way to explain that is from an increase in greenhouse gases. There's no other physics that can explain that. So then you ask, where's this greenhouse gas coming from? Well, we know the answer to that too, because carbon comes in different flavors. These are called isotopes.
Mm-hmm.
Plants like light isotopes, and you see a different mix of these isotopes from fossil fuels. The only way to explain the increase in carbon dioxide that we're seeing in the Earth's atmosphere right now is from fossil fuel combustion. It's not from volcanoes, it's only from fossil fuels. So point A, we know the only way to explain the temperature pattern is from greenhouse gases. Point B, we know the only way to explain the greenhouse gases is from fossil fuel combustion. Case closed.
Okay.
So this is the reason why, and those 2 points, by the way, there's essentially no serious contest to those 2 points in the literature. There's a lot of nibbling around the edges, but no serious debate.
Okay. On that note, we're going to end our first segment. So we are now ready to take questions from the audience or any that we've received from our live stream audience. So if you have a question, please raise your hand. We have folks with mics. I want to ask you, do you ever get discouraged?
Do you ever get discouraged? I am an optimist on this issue because we're lucky that we're living in a time when we can measure the problem, we can characterize the problem. We've seen major shifts in public opinion towards solutions. And fortunately, I think we can make a transition to a more sustainable energy supply. What does discourage me is the fact that the really smart people are really, really good at burying their heads in the sand.
Mm-hmm.
So that's the discouraging part.
Yeah.
So every alternate day, so on Tuesdays and Thursdays, I'm discouraged. Mondays, Wednesdays, and Fridays, and I'm an optimist.
You feeling better? Okay.
Yeah.
So we have a question?
In California, if we're going to get less snow and possibly more rain in the mountains coming down, and the snow that's there melting faster in warmer springs, then in order to prevent flooding and in order to not have that water go out into the sea, aren't we going to have to build more dams and reservoirs? I mean, I know as most environmentalists here, more dams, and they shudder, but I don't know what else the solution would be. So could you talk about that a little bit?
Sure. So this comes down to a classic supply and demand issue. So one way of beginning to address this issue is to lower the demand on the system. One of the other reasons why I've been particularly heartened this last year is to look at the response from California. The governor asked us to lower our water usage by 25%. We hit 28%. So it turns out that it's hard to beat that number much further in terms of usage, but someone described the usage in San Francisco as looking like it was Australia-like in terms of the degree to which San Franciscans lowered their water demand. So, no, it didn't, but that on the usage side in urban areas really was heartening. So we can tackle the demand side. On the supply side, we're losing one of our major water banks. We may have to go to other sources of water. So there's an active effort now at Berkeley Lab to look at driving the price point for desalination down to the point where it's as cheap as other sources of water. This is a solution that also has environmental consequences. I think collectively as a society, we're going to have to look at the positives and negatives as a system and think about this rationally. There's a bit of a tendency, I think, for someone to propose a solution and to treat this like it's a shooting gallery. So you shoot down that solution and the next one pops up and you shoot that one down, wait for the next solution to pop up, shoot that one down. That's not going to work. I think I'm confident that we as Californians can look at this as a whole and figure out a solution that's going to work. And we've looked at this problem out to 2050, and we think there is a pathway to a sustainable water system that will work. So I'm also confident in a solution there. Next question.
Okay, we have a question up here.
Yeah, so this question has come in from our online audience, and I'll paraphrase a little bit. Do you have any advice about how the human species can wake up to how they are detrimentally affecting the Earth and be willing to change its behavior?
It's a really good point, and I think it's an issue that we'll have to come back to. Yeah, so we're not going to solve this problem by just all adopting screw-in LED light bulbs or by stopping flying. We as a species are going to have to change our attitude about how we interact with the Earth and take cohabitation with the web of life much more seriously. This is an issue that I'm starting to talk about with colleagues at Berkeley about how we affect change in attitude. But this is going to take a long time. And I have to say that scientists like myself are going to have to be part of that solution. But this is something that we're going to have to do in concert with people who think about advertising, think about climate equity, think about the arts, think about all the ways that you can affect change in people's attitudes. It's going to be a system-wide issue.
Okay, thank you. Oh, we'll take one more, yes. So then, quick one, please.
Okay, well, I'm hoping that you could talk not just about California, but particularly in terms of loss of glaciers. I'm worried very much about the Indus River and the other glacial sources of water throughout the world, which seem to be affecting a lot of population, much more even than California.
No, you're absolutely correct. There are on the order of 2 billion people who rely on water sources which are drawn in large part from glacial melt. And that's a water bank that was put in place with the formation of the Himalayas, and so it's been in place for tens of millions of years. And that water bank is going to be seriously stressed by climate change. that is an almost unique challenge. And the way that's going to have to be addressed is a worldwide engagement with Pakistan, with India, and with China, and one in which we go to them with open arms, really an open extension of what we've discovered as best practices, and then draw from them what they've done to meet this, really, it's truly a Himalayan-sized challenge. But that's an area where water, you're going to see how much more valuable water is than oil once that becomes a stress point in that part of the world. Because you can't drink oil. I mean, you have to drink water, and people are going to really realize how acute water is as a resource once they go to draw from that tap and nothing comes out.
Okay, thank you. We're going to move on to our next section now. This is sort of the predictive part. So we closed the last segment with a look at the California snowpack. But I'd now like to sort of step back again and think about the whole snow and ice issue from a more global perspective. And I believe that we have a new video just from we received today. So why don't you tell the folks who were watching online as well as those here what exactly we're seeing in this animation here.
So we're looking at an animation of the Earth. This is drawn from data that was collected by NASA at 1 kilometer resolution globally. So there's 500 million pixels in each image that are going up on the screen here. And this is the annual cycle in snowpack as we currently experience it. And this is again, a major bank of water that we draw on every year. What this image is supposed to, I suppose, convey to us is first the kind of capabilities we have now for measuring the climate system. Also, how much the planet looks like a breathing entity from space. If you watch the annual cycle, it's really quite striking. And third, you can see from the perspective when we zoom in on California, the huge annual cycle in snowpack that we rely on over the Sierras, and that in the last couple of years has almost gone away.
So let's talk about how this was made and sort of the predictive capability of supercomputers and the like that we have at Berkeley Lab and other institutions as well. So how are these models actually developed? What kind of data is put into them and how much has to be crunched?
Sure. So just starting with the satellite imagery alone, because my group does a lot of work with the satellite imagery. So the satellites that we rely on now are delivering close to probably in the range of 200 to 300 terabytes of data per day on the climate system that we're using to monitor its health. And we analyze years and years of that data to produce imagery like this. We're now building models that can emulate the Earth at the same resolution. So we're in the process of developing models that literally can model and simulate the climate down to the scale of 1 kilometer. And what that means is that once we bring those online, we'll be able to look at the variations in microclimates within the Bay Area, which is really a remarkable new capability. And we think we'll be able to do that in the next decade.
Well, I'm a believer, but there may be some who are skeptical about this whole stuff. How can we be sure that what you're modeling is actually accurate?
Sure. So one of the things that we do is we build these models so that we can run them as weather models and test them directly against observations of the climate and the weather as we experience them. And so increasingly we're building models that are known as unified models. We can run them as weather models, test them against observations from aircraft, from the surface, from space, and then flip them into a mode where we can use them to predict the climate. And that's it's the acid test of whether or not a model is trustworthy, whether or not it produces the weather that you're seeing through your window pane. And that we're building models of that class.
And so when you get information, as you mentioned earlier, about the melt in Greenland, is that incorporated in some fashion into the models so that something is happening faster, for example, than you anticipated? Is that an element that you include?
We are just now building models for the ice sheets that have that capability, so that we're much further along in sort of the weather that we see outside our window than we are with treating the ice sheets. But we are building models that can directly assimilate observations from space and from aircraft. And we're building the observational capability also to monitor these huge ice sheets from space.
I mean, do you have, when the models are, I mean, they're very impressive to look at, but do you, when you show them around and send them around, not to the scientific community, but to others, are there people who just accept what they're seeing as gospel, or do they continue to question it?
Well, as a scientist, I hope they don't accept them as gospel.
Okay.
I mean, they're designed, the whole point behind these models is that they're imperfect representations of reality. I build them for a living, and I don't trust them completely. I think we have to subject them to rigorous tests, and we have to be, frankly, I think the best way to be a proponent of them is to be more skeptical of them than anyone else.
Okay.
And we build that skepticism into how we conduct our research and how to make them better.
And could we take just a moment to do a little Berkeley Lab thing and talk about our supercomputing capacity?
Sure, so absolutely. The Berkeley Lab has had a computer center that's been used for climate research for over 30 years. During that 30-year time frame, the computers have increased in speed by a billion-fold. We're in the process of installing the fastest computer available to the US scientific community. That'll be installed later this year in October. It will come online then. A number of us can't wait to get our hands on it. And it's being installed in a unique facility that's just opened up on the Hill that's one of the greenest computer centers on Earth. It was designed to use the hill and the flow of air down the hill as a natural refrigeration mechanism. It's a remarkable building. So we've built our environmental values into the very computer center that we're using to predict climate change.
There you have it, folks. All right, we'll take applause. We'll take some applause. An element of this modeling, the rainforests, which we hear a lot about. So what do the models tell us about that? And I know there's an effort by the Department of Energy to study that exact issue.
Right. So the rainforests constitute a very important, they're a gigantic source of environmental diversity. So they're a treasure just in and of themselves because of the huge range of species they contain. So I think aside from what they do for mankind, we should be treasuring for the fact that they're a representation of just how remarkable life is on Earth. So I think we should pause and appreciate that for a moment. That said, the other thing that they're doing for us is that the great forests on Earth are drawing down a quarter of the carbon that we emit into the atmosphere every year. So they are reducing, this is what's called an ecosystem service. They're basically offsetting, by acting as a sink for carbon, they're offsetting some of our emissions. The Department of Energy looks at this through the lens of, wouldn't it be unfortunate if that sink of carbon dioxide went away? And so we are very focused on understanding how the forests on Earth are going to evolve in a climate they have not experienced since these forests really some of them were established, or at least established in their current form. And this is a major challenge for us because we're moving out of our comfort zone of modeling the Earth's weather. This is something we have a lot of experience. We're now having to model something that's as complex and diverse and remarkably rich as a forest and predict how it's going to operate in a situation where we can't even make measurements of the conditions it's going to be operating in. And so that challenge of how to sort of take measurements today and then extrapolate to our future climate, this is front and center in our work right now at the laboratory.
Okay, well, let's move to California forests for a second and to our redwood forests and this whole issue of fog, because I know there's a fog expert in your group. And I actually talked to him, and it was the complexity of that. I actually did a story once about fog. It's very, very difficult to model, I would imagine. So we have another animation produced by Berkeley Lab about water vapor showing. So what are we seeing here? And I want to use fog as a way to sort of jump into this whole water vapor issue and how it is, and what we need to know about that.
Sure. So what we're seeing is an animation that was produced at Berkeley Laboratory showing you water vapors. The white in the imagery is water. And you can see how beautifully it tracks the storm fronts and storms, for example, like the Pineapple Express that brings water to California shores, the huge cyclones spinning across the Pacific Ocean. Water is the biggest greenhouse gas in the climate system. It's vital to life on Earth. It's vital to the California ecosystems in very many ways. And it's vital to the redwood forests that we enjoy here and that are critical to our ecosystem. We are trying to understand, based on measurements that have been taken from airports that have been in existence up and down the coast of California now for decades, what's happening to the fog bank in California and how it might evolve in the future. And this has big implications not only for the redwoods, but also for our coastal environment.
Mm-hmm.
Modeling the fog accurately is right at the limit of what we can do presently. And so we're really hard at work, and we hired an expert in modeling fog precisely for this reason, in order to understand how our coastal environment might change. And this is a big target for our research going forward.
So would that fall into the category of climate change or abrupt climate change? These are two terms that are sometimes used interchangeably. So
Sure.
What would be the defining line between those two?
So climate change is something that happens gradually.
Mm-hmm.
Abrupt climate change is defined as something that happens quickly, and the term quickly is a little loose there, but it occurs quickly and over a big region. So an example of that would be, let's suppose that we suddenly caused one of the big ice sheets on either Greenland or Antarctica to slip and just start racing toward the ocean. That would be in a form of abrupt climate change. Another form of abrupt climate change would be if we caused the oceans to change the circulation pattern on a fairly quick time scale. These would be large-scale, long-lasting, very hard to reverse forms of climate change that would have impacts for millennia.
Okay, yes, so we're going to skip around a little bit because I failed to ask about food supplies. We've talked about water, so clearly there's an implication for our food supplies. So let's talk about that too. We will get to hope, I promise.
Yeah. So our food supplies are being stressed partly by climate change. There's a demand issue here, coming back to this issue of supply and demand.
Mm-hmm.
So we've been riding this amazing, escalator called that's based on our ability to produce fertilizer. Mm-hmm. And part of that's based on our ability to deliver phosphorus to crops that desperately need it to grow. We're going to run out of easy phosphorus by the middle of this century. So that's going to be a big issue with regards to fertilizer. That's going to have an impact on our ability to produce food to sustain the world's population at that time. At the same time, and again, we're going to come back to hope, I promise, but we are going to be, we know now based on enough information that heating crops up tends to lower their productivity. This is now being worked on a lot. We are supplying them with more carbon dioxide, which acts as a natural fertilizer, but we're stressing them as well. And we've got to deliver water to them. And one of the places actually that's facing a bigger challenge than California is the breadbasket. The breadbasket has been drawing on pretty much a single source bank, which is aquifers that have been in place there for tens of millions of years. And they're drawing on them fast enough that they're causing measurable changes in the height of the Earth that we can measure from space, thanks to the rate at which they're drawing on that water bank. So we're going to have to come to terms to that. And again, there are solutions, but we're going to have to face them squarely and have an adult conversation about them.
Okay. So from land to air, when we see really horrible pictures of the air pollution from around the world, we tend to emphasize carbon, but what we haven't discussed so far is something called the short-lived climate pollutants, the soot and methane. Let's concentrate on those.
Sure.
So how big a problem is black carbon or soot? And then we'll talk about methane a little separately in just a second.
So soot is really a bad actor in multiple ways. It is a major cause of respiratory disease. And a report was just issued at the American Association for the Advancement of Science meeting that was held in February that estimated that 5 million people died in 1 year due to these short-lived climate pollutants. So this is a serious human health issue, and soot is a major actor there. Soot also absorbs sunlight, and when it absorbs sunlight, it acts to heat the climate system. It is unique, really, among the short-lived climate pollutants is that it absorbs sunlight so strongly that it can heat the climate locally and to an appreciable degree. And it also decreases crop productivity. So there are multiple reasons why soot really, we need to take soot out of the system. There are no benefits from having it in, and there are a lot of benefits from taking it out.
And primary sources of soot are?
Two primary sources, both of them related to combustion, so fossil fuel combustion and also biomass burning for cooking, for example. Every evening in Southeast Asia and India, 200 million people boot up fires in their homes made, and for very good reason, this is the only way they have to cook. But they have very inefficient combustion that's producing a lot of soot. They have to do this in order to feed their families, but it's a major source of soot pollution. The good news here is that soot has a very short lifetime in the Earth's atmosphere. So if we got a handle on it, on both the combustion sources from fossil fuel combustion and from cooking, it lasts in the Earth's atmosphere for about a week. So we can take it out of the climate system just as quickly as we put it in.
Okay. Now methane.
Yes.
Pernicious methane.
Pernicious methane. Man is now the major source of methane in the climate system. We outrank natural sources by a factor of 2 to 1. The two dominant sources of methane in the climate system and from man are, again, from fossil fuel production recovery, for example, from coal mines, and from agricultural activities. Again, fortunately, methane has a relatively short lifetime in the Earth's climate system. It's less than a decade. And we're starting to see concerted action in the United States. President Obama has made it a central tenet of his climate action plan to get a handle on methane sources. And we've also seen action in Asia and around the world in trying to get a handle on this problem. Japan is experimenting with rice paddies, for example, that emit much less methane than traditional inundated rice paddies. So countries around the world are really facing this issue very squarely.
How does it rate with carbon in terms of its intense damage that it does?
So methane is about, in terms of its total impact on how much we've changed the Earth's greenhouse effect, it's a third as big as carbon dioxide. But the problem is that it's 30 times more effective pound for pound than CO2 as a greenhouse gas. So, in this country, we're really touting methane and natural gas as a wonderful source. It is wonderful. It produces half as much carbon dioxide as per BTU as coal. So that's wonderful. That's a great advantage relative to coal. But because of this 30 times fold intensity of its greenhouse effect, you cannot tolerate leaks in the system. And the U.S. has built an energy infrastructure around recovering and delivering natural gas that is highly leaky and is very poorly characterized. And we now know, thanks to measurements made in part at Berkeley Lab, that there's twice as much methane being emitted over the United States as EPA claimed. This is despite the fact that EPA has been very hard at work at this problem.
So twice.
Twice. And we should be very grateful to EPA for having tried to characterize it, but there's twice as much there as they thought.
And what role does fracking play in the methane situation?
We've literally reinvented the Wild West. But this time around, the gun that's facing us it's a loaded gun, but it's a loaded gun that involves natural gas. And I think we have to get a handle around the leaky sources of the methane and the very leaky delivery system, because otherwise the benefits from natural gas are largely offset by these leaks into the Earth's climate system. Let's just look at what happened in Los Angeles. Los Angeles had a leak that equaled essentially all the cars on the streets of Los Angeles during the period when that leak was active. And this is a leak from one single reservoir of natural gas. So that sort of sets the scale of the problem for you.
And on that happy note, we're going to end the second segment.
Yeah.
So, do we have any questions in the audience? Please raise your hand.
Questions on, yeah. Yeah. So there's a request to amp me more. Are there questions for the content?
Yes, questions for the content?
Yes.
In the climate models,
Mm-hmm.
I've heard that there is a lot of methane up in the Arctic that will be released as the
Yeah.
permafrost is melted. Is that methane release incorporated into contemporary models? Because I heard that it wasn't in past IPCC models.
Right, so that the capability of modeling that methane has been coming online. We did a lot of research on that at Berkeley Lab. I'm proud to say that we were the first group to build a fully prognostic or predictive methane cycle for use in climate models. The challenge there is that there's a huge amount of carbon stored in permafrost. It's 10 million square kilometers of frozen soil up around the Arctic Circle. According to certain estimates, twice as much carbon locked up in that permafrost as there is in the Earth's atmosphere. So the critical question is, how does that methane come out, as carbon dioxide or as methane? One thing, so there are a number of groups worldwide that are now measuring this. I am happy to say that the measurements suggest that the majority of that, when the permafrost thaws, the majority of that carbon is coming out as carbon dioxide, not as methane. But it's still an issue. And it's something that the Department of Energy and the National Science Foundation and actually all the member countries in the Arctic Council are hard at work trying to solve. And we are bringing those capabilities online in the climate model. So that's becoming a real life capability now. But excellent question.
Live? Okay. Hey, is Brazil making any progress in saving the forest? And is Indonesia making any progress in the burning of their forests?
So I'm happy to say that Brazil has become, over the last several decades, a major player on the worldwide stage in climate research. So they are working shoulder to shoulder with countries around the world on characterizing the problem. They are also aware of the issues around logging the Amazon. One of the things I am encouraged that they're doing is they're trying to bring back the Atlantic range. The entire coastline of Brazil used to, 30% of it was forested, and they cut that down to about 7% to make way for cattle. They're now trying to bring back that rangeland. That's a decades-long project, but that is a project to which they are devoted. The issue on logging and destruction of the Amazon continues. And Indonesia is another area where the burning of their forests continues to be a very real problem. Both of these are, we're going to come back to issues about how you solve these problems in an equitable way. The way to solve this problem is not to tell them, don't do this. You have to figure out a way where the people who are making money and making a living off of a destructive activity are provided with an option for a constructive activity. And I think this is something that will become a theme, I think, throughout this evening. How do we switch? How do we, this can't be, do as I say, but not as I do. It really has to be a situation where we work with them to find a constructive way for their population to make a living.
Okay, thank you. We're going to now move on to our third section. We're going to zero in now on the Bay Area.
Mm-hmm.
So we're already experiencing king tides.
Mm-hmm.
And I think you will agree, but I want your opinion about the Bay Area being sort of a microcosm of the climate changes that we're about to see.
Mm-hmm.
We have a coastal city. We have major agriculture nearby. We're a major transportation hub.
Mm-hmm.
So do you feel that we're special in any way, or are we actually representative of the kinds of things that are going to be happening when we talk about climate change?
We are representative in a couple different ways. One of them is that we have we share a coastline with half the rest of the population of the United States. So in that sense, we're right with the close to 170 million people who live within 5 miles of the coast. So that's something that we do share with them.
Mm-hmm.
We share with them the challenges that are attendant with that in terms of sea level rise and the effect of storm surges on the coast. The other thing that we share, in some sense, we're a microcosm of this, is that we have a very loosely federated government here. So you could imagine a bunch of reasonably well-intentioned people, but there's no central actor that's saying, this is how we're going to work in concert. And so the question is, how do we, as a loose confederation of 9 counties, 100 cities, pull together to do something intelligent around climate change?
So that we don't have to have seaplanes to land at SFO?
Yeah. Well, storm surges combined with king tides, combined with 1.5 meters of sea level rise, will do a number on the coastal infrastructure in the Bay Area.
Okay, so let's talk about the Climate Readiness Institute, of which you are director. So what exactly is it? What is its mission? And what are its hopes?
So the normal thing for me to do as an academic would be to set up a think tank. And we thought, okay, that's very nice, but we need some action. So the Climate Readiness Institute is set up to do 2 things. It's designed to engage the Bay Area universities and labs with the Bay Area very directively and in a very direct partnership to work on real problems that they have. But also in pursuit of those solutions to also pursue the missions of these labs and universities toward training the next generation of activists, training the next generation of scientists, and to further research missions. It really is designed as a both-and proposition.
So who belongs?
So at the moment, 4 institutions belong. UC Davis, UC Berkeley, Berkeley Lab, and Stanford. And we're very proud to have this partnership with these outstanding institutions.
So you alluded to it before. We have this vast governing structure in the Bay Area. So how do you influence policy? How do changes happen?
So the way that we did this was by going on a listening tour. And that's really the first, starting with the message, hi, we're here from academia, we're here to help, is probably not the right way to start. So what we did instead was we went to, first of all, we were asked to engage in this activity. I think that's very important. We didn't start by proposing this as a solution. We were asked to engage. And we were asked by representatives from the Association of Bay Area Governments and other joint planning committees that essentially said, we've looked at the problems that we're facing. Some of these are so big and require solutions of such magnitude that we're not even sure where to start. And we need the talent base that's fortunately present here in the Bay Area to engage with us on solutions to these issues. So we took that message very seriously, and what we've done since holding our first kickoff meeting actually in this very room was to hold a series of meetings which were split 50-50 between stakeholders and scientists and professors like myself to sit across the table from each other, essentially listening to people who were acutely aware of the problems and people who were aware of what the long-term solutions might look like, to try to come up with areas where we knew we could engage on looking at the big picture. So this is stuff that you can't get from running to a consultant. This requires the full intellectual horsepower of the universities and laboratories around the Bay Area.
So give us an example of some of the things that you learned in that exchange of information, which sounds really interesting.
So we have learned what some of the tall poles are. Certainly the question around water that came up earlier this evening is one of them. How do we deal with the fact that we have a very heterogeneous water supply in the Bay Area, and that portions of that water supply are going to be very stressed over the next 50 to 100 years. How do we deal with that? Another issue that came up loud and clear was issues around governance. How do we provide the Bay Area governments with a framework in which they are sharing a set of common information around what the challenges are, a common set of best practices, and a common set of solutions. Issues around health also rose front and center. This is for a couple of reasons. One of them is disease vectors, which we've been hearing about in spades in connection with the Zika virus, and the vectors that brought that to Brazil. And also issues around heat stress and other challenges that public health providers in the community are going to be facing going into the future. These are all challenges where, just to take the heat stress as an example, we're going to be looking at a situation where heat waves become far more common, even in the Bay Area. And those pose severe stress to us because we have enjoyed an environment where we do not have to air condition ourselves nearly as heavily as people in other parts of the country. We look a lot like France in that regard. And I want to remind people what happened in France in 2003 during their heat wave. It was not a happy outcome. So those are some situations where they came to us and said, help, we have a problem, help us engage. And we have worked with them to then identify a series of white papers on these problems and now seeking funding to go after and support to go after these solutions.
Okay, devil's advocate for a second. Those of us who live in the Bay Area, let's just use transportation as an example. And we talk about regional cooperation. We know that this doesn't really work very well. At least it hasn't in the transportation area. So why should we hope for anything better now? Sure, it's a big problem, but the same issues that get in the way of solutions were still arising, I would think, within any government entities, even working with academia. So how do you overcome that?
One of the ways that we do that is by building networks of best practice. So we've been busy engaging both on this side of the Bay and also with San Mateo County and other county, dealing with water agencies up in the northern part of the county. So we've been sure to engage with communities that ring the Bay Area as part of these workshops to make sure that they are all in the room together. And also to communicate with them and to work on solutions where we look at the challenges as a system. So we look at what would happen if you looked at it, we essentially pose the issue, let's imagine you try to solve this problem on your own, and then imagine you try to solve this problem collectively. These are classic game theory kind of issues. And essentially present to them the case that we're going to be a lot better off if we solve this collectively. And I want to draw on an example that affected the East Coast during Hurricane Sandy, where communities up and down New Jersey decided to go it alone. So some of them built big berms. They were unaffected, but they directed the storm surge directly onto the neighboring township. And that was a disaster because it resulted in this checkerboard pattern of communities that were essentially wiped out. We don't want to go there in the Bay Area. So we are presenting that, compare and contrast scenario to governments around the Bay Area.
Is there any role for an individual to play in the Climate Readiness Institute? You mentioned the training for students and stuff, but for others at this point?
One of the issues that we take very seriously and we're beginning to explore is the issue that came up earlier this evening around attitude change. Again, we're not going to solve this problem with a bunch of really smart people coming up with technical solutions. This is going to have to be addressed as a community in partnership with our neighbors. And so the Climate Readiness Institute is now beginning to discuss with journalists, with social scientists, how we bring best practices that have been learned around issues of public health to solving the climate issue. I mean, I'm happy to say that in this country, we've gone from a situation where smoking was very common to now where it's really frowned upon incorrectly. We want to take the same strategies that worked around issues of public health and around diet. I mean, compare and contrast what we have now in our grocery stores to what we grew up on. That's another example of a success story. We want to bring those practices to bear on climate change. And that was in large part succeeded because we communicated to people that their children's health and their grandchildren's health critically depended on changing the way that they behaved. And I think we can succeed again.
Okay, there's another element that you mentioned earlier, and that's the issue of climate equity. So we do have an image that we'd like to show. So you could tell me what we're seeing here and the disproportionate effect of all of these issues on more impoverished communities.
Well, the Bay Area is fortunate to have 7 million people living in it. And the challenge that we face is that the solutions that we pursue really need to work for all of the 7 million people. This cannot be one where there are a few winners and a lot of losers. The picture that's shown here is an issue that has faced us because of historical habitation patterns in the Bay Area where Some of the ports grew up on labor, fairly poorly paid labor, that's now stayed in place around those ports. Those ports happen to be at sea level. So the people who are living next to those ports are at ground zero for the effects of sea level rise. They are some of the people who are least able to pick up sticks and move. And so the solutions that we come up with have to address this issue of an historical inequity where that labor, built the bay into what we have now, brought us much of the prosperity, but we cannot leave them behind to then literally be inundated by the consequences of that prosperity.
So what do we do?
We have to figure out solutions for climate change and for mitigating climate change and for adaptation that bring co-benefits to everyone. And to give you an example, let's talk about carbon dioxide for a second.
Okay.
That's the chief culprit in this whole climate change issue. And by the way, the carbon dioxide level in this room is elevated well above ambient levels right now because we have a lot of very, very smart, dedicated people in this room thinking about climate change, but you've elevated the carbon dioxide in this room to probably a couple of hundred parts per million above ambient at this point. Mm-hmm. If I were to take it back to ambient levels, none of you would be the wiser because you can't taste it, you can't smell it, you can't see it. But what if I did that at the same time as bring you greener parks, better transportation, so that if you're juggling 2 jobs to try to make enough money to raise your family to a higher standard than you had as a child, you had a decent transportation system, made sure that your kids' schools were much greener. That's a co-benefit. Mm-hmm. And we have to make sure that the measures that we bring to bear on climate change are part of a system that brings in co-benefits so that people can see immediate tangible benefits to their own lives, to their families' lives, at the same time as we solve these larger issues. And that's something we've been thinking about hard as part of the Climate Readiness Institute.
Okay, so that would be the Climate Readiness Institute is one component, but when you think about the larger intellectual infrastructure and research infrastructure in the U.S., I mean, are we really aligned properly to meet this problem, or do we need to do some major structural changes in that?
No, we are not aligned properly to deal with this problem. Let me just compare and contrast the amount of money that the U.S. spends, and I don't mean to single out the U.S. on this issue, but the amount of money the U.S. spends on weapons R&D versus climate R&D, it's over a factor of 10. So the U.S. spends somewhere in the range of $70 billion a year on weapons research. And if you look at the sum total spent on climate, it's just around 6. It's a factor of 10. So writ large, at the level of the nation, we're not spending nearly as much as we should. We should be looking at this as if this is a Manhattan project, but a Manhattan project with a worthy outcome, and one that's going to take a century to play out. But we need to be dedicating resources to it as if it's that scale of challenge.
I want to get back to the heat wave example just for a second, because I think what we might see when we're talking about climate equity is the possibility that in substandard housing, that's also sometimes an issue, like there was in France, massive heat waves, there could be people dying as a result of that, and that would be disproportionately happening in these underprivileged areas is what I'm assuming. So the slide that we're showing now is, I think, projected heat wave possibilities in the Bay Area in the years ahead. So this is a serious threat, I would assume, at this point.
Yes, it is a serious threat, and this is one where the climate models are in complete agreement about what's going to happen. There's really no ambiguity. The only ambiguity is that most of the climate change we're going to see between now and 2040 is already in the pipeline. What happens after 2040 is really something where we have a major choice about which path we follow. If we choose to follow business as usual pathway, we're going to be looking at a situation where the southern part of the United States is experiencing permanent, perpetual heat waves every summer. That would be a serious threat to human health. This is an extremely robust prediction. This, by the way, It affects not only the United States, it affects China. So the Berkeley Lab has taken this result and shown it to the previous premier in China. It affects the whole Mediterranean area in Europe. It affects the whole Northern Hemisphere. So this is an issue that we have to face squarely, because it will be, and again, we're sort of framing this in a human context, but we also have to think about the implications of this for ecosystems. We've sort of punched the accelerator in terms of how rapidly ecosystems have to change to meet a very different thermal environment. And some of them can't change fast enough. So this is a situation where, we keep putting this in a human lens, but humans, we cohabit this planet with a really remarkable diversity of life, and we have to be mindful of the fact that we're stressing them out as well.
This is the web of life that you mentioned earlier.
Yes.
So the adaptation, when we hear that term, we're usually speaking about the human ability to adapt, but not necessarily the other part of the ecosystem which we are destroying by this turn of events. Okay, I think we're going to end the segment now to stay on time. So for those who might have questions now about what we've just discussed, or maybe something earlier, that's fine. Please raise your hands.
So I really appreciate you seeing all the climate modeling you've been doing, and I'm wondering if you are partnering with other organizations that are actually doing modeling about human behavior, because it clearly we're not ready. You keep talking about business as usual. Well, given looking at our country today, we're clearly not ready to do much about anything. So let's say it takes us 20 years to ramp up to start to be a little bit more cognizant of our behavior and really support some of these changes. Let's say it takes 20 years. That's probably really optimistic. Has anybody done any modeling to say, okay, if it's business as usual for the next 20 years, then what are we going to be facing? Aren't we already at a tipping point where we can't wait? No.
The scientific community is working very hard to tell policymakers what the window of opportunity looks like, and that message is being constantly relayed to them. So I'm happy that you asked this question. There is a window of opportunity. We have quantified that window of opportunity for them, and we've told them how much time they have to get it together. That they still have a chance to get it together, but that get it together time period is about one human generation long. So the price, coming back to this issue you raised earlier about the cost. So if you're worried about the cost of switching energy sources, just wait till you look at the cost of delaying the solution, because that cost becomes incredibly high the longer you wait. To come to the other part of your question, then I want to take the question over here. Yes, we are. I'm a physicist by training, and so I get nervous when I have to get all touchy-feely. But
That's okay, Bill. We like that.
But we are, so most of our climate models, they are models of things we can measure with a thermometer. But we Berkeley Lab are one of the two labs two groups on Earth that have now built a joint human climate system and are starting to look at the interactions to understand really what scenarios get us to, how do we land on our feet like a cat? And we're starting to look at that with this model.
Okay, another question from the audience?
So, kind of on the subject of hopeful elements in this whole discussion, you talked a little bit kind of parenthetically when you're talking about climate engineering, about generating clouds with high reflectivity. I was wondering, as one example, if the water vapor content of the atmosphere increases, would general cloud cover increase? Basically, are there any natural negative feedback loops? There are lots of scary positive feedback loops, but what are what, if any, are the negative feedback loops of climate change that nature has to offer?
There are negative feedback loops. The problem is that they operate on really slow timescales. So, you can go to the Grand Canyon and see a beautiful example, just walking from the rim down to the Colorado River. sort of play back the tape of climate change. And you can see the action of these climate feedbacks play out in front of your eyes. The climate feedbacks that will draw down carbon dioxide, there's some fast-acting ones, things like trees. There are longer-lived ones like the ocean. The ocean contains 50 times as much carbon dioxide as the Earth's atmosphere. That takes 3,000 years, though, to do its work. And then you've got geologic ones that take tens of thousands of years to do their work. It's thought, for example, that one of the reasons why we were able to form Antarctica is that the formation of the Himalayas acted as a gigantic fractal sponge for carbon dioxide in the Earth's atmosphere. That's a feedback that took tens of millions of years to act. So there are feedbacks, that's the good news. The problem is that we have punched the accelerator in terms of introducing carbon dioxide into the Earth's atmosphere. And we're currently operating at 10,000 times what nature normally does. We're about to hit 100,000 times. So we're going to take the climate back this century, the Earth's carbon dioxide level, back to levels it hadn't seen for 30 million years. And those feedbacks just don't operate quickly enough to handle a situation where you're driving toward the cliff and you decide to floor it. So that's, yeah.
Okay, last question for the evening. Who will it be?
Scientists at several different universities tried to look into the question about carbon intensity of food and see what made the food more or less carbon intensive. And all of them came to the same conclusion, that the main contributor to the carbon density was not the shipping, but the production of the food. And that in effect, if you were to eat apples shipped from halfway around the world, it would be a far lower carbon intensity than if you were to eat locally grown beef.
You do have a point there, and I wasn't. I was trying to dodge this issue about protein selection.
We're back to vegetarianism now.
We're back to vegetarianism. No, I think but one could equally well. I want to pose the same question with respect to our, the Pacific Rim. Look at the impacts of cultures that are devoted to fishing in a completely unsustainable way. I mean, we're as a planet going to have to shift cultural practices around food, and these, you raise a perfectly good point. This is the reason why I mentioned that I went from being a vegetarian to a vegan, so imagine why I went to being a vegetarian. It's partly for that reason as well. We're really going to have to think very consciously, and frankly, we're not going to have a choice anymore about how to live sustainably on this planet. And the issue, I want to, again, broaden the lens back from just what we eat, because this is a favorite topic. But we also have to think about how what we eat affects the web of life around us. And we need to move to a mode where we're thinking about, we need to move to a mode where the fact that we've killed off a species is headline news above the fold on the newspaper. This has to be something where, again, we need to internalize the idea that the web of life is really precious, and the loss of a single salamander species trumps Trump.
And on that note, we will close. Thank you, audience. Thank you, Bill.
Thank you.
Thank you all. We hope to see at least some of you in San Francisco on June 1st at our next Science at the Theater, and I expect to see you all talking to your grocery store managers tomorrow about carbon footprints. Thank you all very much for coming. Good night.
Good night.